All right, this is much better. Thanks for the introduction. It's great to be here. It's always great to be in New York. I have very deep connections to this city. It's great to see old friends here from Brown. Today I would like to talk about not about theory of visualization, but I'm going to talk about an approach to visual analysis of large collections of genomic data points. Okay? And I'm going to do that through a prototype tool called invis. It's a prototype tool, but I think it's going to make our points. So when I started thinking about visual analysis problems in genomics, which is like more than a year ago, I talked to almost everyone on campus at Stanford doing genomics. And during those conversations, this paper came up. It has a very catchy title. And I found it funny a little bit. Sequence first, ask questions later. Arian Sido wrote this paper it's a viewpoint paper. He wrote this paper almost 10 years ago. I think he was very excited about the great potential of high throughput sequencing. And the point was that if we collect large amounts of genetic data, we can transform biomedicine. And the reason I like this paper is more than anything else is title. The title reflects the current data-driven research in genomics, right? So, and we have seen actually developments last 10 years to realize or to test this vision, right? Led by mostly international consortiums, people collected large amounts of genomic data. And these developments were not actually limited to academic research. Now most of you know that there are commercial companies that are providing personal genomic services. On the way, they are collecting lots of personal genomic data, right? And I believe this is mostly driven by the cost. The cost of sequencing decreased dramatically in the last 10 years. And I think last January, Immuno introduced a system, arguably, that reduces the cost to $1,000. Right? So I want to go back to this thing, asking questions later, right? So if you think about, that's my observation, I might be wrong. If you look at the existing tools in this domain, there are excellent tools if you want to inspect one or single genome or few genomes in depth. Right? But if you don't know what questions to ask, or if you want to compare and explore not one but thousands of genomes, actually there are not many tools out there. But those tools are very good. The existing tools are very good again for exploring single genome in depth. Well, I mean, this makes sense because existing tools, this is one of the typical cases, right? It's a fast-changing field where much of effort goes to or went to data collection, right? And data analysis, whether visual or not, lag behind. So in response, I mean, if you want to explore actually thousands of genomes at the same time, there aren't many tools out there. Right? So in response, we developed invis. Invis is actually, in many ways, the first interactive visual analysis tool that lets you to explore thousands of genomes simultaneously. So this is a prototype tool. It's not, it's open source out there, but you need to engineer to make it really, really useful. But I'm gonna, again, this was our workbench to implement our ideas. So the first prototype was based on the data coming from in vitro selection experiments. Let me introduce what is in vitro selection. So one of the important questions in molecular biology and biochemistry has been whether genetic research can be possible without using living organisms. Right? And in vitro selection is a confirming answer to this question. With rapid cycles of growth and selection, this method biochemically simulates Darwinian evolution. So by construction, the data sets from these experiments form a large high-dimensional space. And therefore, it is difficult to really for biologists to make sense, explore, or interpret. So we are using invis to explore data sets from in vitro selection experiments. And those data sets, again, include thousands of genomic data points. I'm going to talk about a little bit design of invis. Right? Again, this is more like our CS, computer science viewpoint to the data visualization. So try to be patient. So the first step in our design is to collect user tasks, right? So go and talk to users and try to understand what they are trying to accomplish with the data. They are not going to give you direct answers all the time. Right? The goal is to infer those tasks rather than get those tasks from users directly. Then based on those tasks, in general, it is almost impossible to take the raw data and directly visualize. You need to prepare the data. That's what we call as data transformation. So, and based on user tasks, we design visual encoding. How are we going to visually encode, represent data sets? And of course, interaction design. So I'm going to go and a little bit talk about in detail about each element here. Let's talk about user tasks. So in our collaboration with biologists, we identified basically 4 high-level tasks. In this specific case, I mean, they make sense, but let's see. I don't want to do it too fast, but yeah, those 4 tasks make sense. But in general, what they want to see with this data is they want to see the variance in differences between sequences. They want to be able to explore possible any potential evolutionary pathways between sequences. So let's talk about a little bit data preparation. So we have this raw data. Basically, length is around, which is different from human genome. It's going to be a main challenge for us to take this invis to the next level. But this data set has more or less around 200 base pair length sequences. So in some ways, it makes our job is very easy. But anyway, given data sets, often those data sets come with a reference sequence. Even if you don't have a reference sequence, you can indicate one of those sequences as reference. Right? Given a sequence, think about like 10,000 RNA sequences. We indicate one sequence as reference. We pairwise align those sequences to reference and filter out too long and too short sequences. This is based on our collaboration, our collaborators' feedback. So we didn't want to include too short and too long sequences. So we filter them out. Filter, and then pad the sequences to have the same length. Padding means like putting gaps. So we use pairwise alignment, not a multiple alignment, because we use a pairwise alignment. It was much faster. Okay. This is transform data. Let's look at the user interface a little bit. All right. So the main point with invis or with this approach is that I'm going to show you a global view of the data along with the local view. And you are going to be able to explore both the local view, individual segments, as well as the global space of the population data. Right, we have global view. In this case, our global is basically a scatter plot. Each circle in that scatter plot represents a sequence. And the layout also reflects the similarities, genetic similarities of RNA sequences. I'm going to talk about how we obtain that. And we have, around this global view, we can put local views, individual sequences, as well as future views. And of course, there's a space between global and local view where you can explore that space using interaction. So I'm going to talk about a little bit how we obtain this representation, the global view representation. Okay. Again, individual node, individual circle there represents a single sequence, and their color encodes the origin of their population. Right? But the idea over there is that their layout in the space, in the plane, represents their genetic similarity. mutation similarity. So how we obtain the scatter plot representation? Given the sequence, we encode numerically. Right. So numerical encoding right now is somewhat arbitrary. So a good question to ask at the end is, whether that encoding matters or not. Then we run PCA, principal component analysis on the data, the raw data in this case. You can use anything else, any dimensional reduction method. We use PCA and use first two principal components as x and y axis of the scatter plot. Okay. All right. Here we have three different populations. One preselection population, three different populations. I'm going to talk about a little bit those the local waves. Again, those encodings or those visualizations are not new in some ways. Their configuration is new. So basically, we have a heat map wave, which is a heat map. The primary function is to provide on-demand access to any individual sequence. So basically, heat map in this case, the reference doesn't change, which represents the reference in the. Let me see if I can point here. Hope not. All right. Oh, all right. Anyway, so the reference sequence is that the circle with filled with white color, and so here our simple heat map view, which shows that reference never changes, but when you move the mouse over another sequence in the global space, it's going to update the current sequence. So you can easily, next to each other, you can easily see, the difference between the reference and the current selection. And of course, there's interaction, Gaussian linking. I'm going to talk about that a little bit. And the other representation we use in this case, stack bar representation, which basically represents different statistics over populations with respect to the reference sequence. All right. So there's any given base pair point, right? The length is a baseline. The length of the bar above that baseline represents the ratio of sequences that have the same base value at that point with the reference. And the distribution behind the baseline represents a difference in frequencies. So you can think about it as like a mutual information, but visually represented there. All right. Simple introduction. Show you Gaussian linking. Let's start with Gaussian linking. Let's see if I can play the video. All right. No, I don't want to do that. Yes. So we are using D3 as well. The main idea is that when you go over here, right, your reference sequence, I can interactively show you what other sequences at a given position are different from the reference sequence. Right. Again, this is related to one of the tasks that we got from our collaborators. We would like to see the differences or similarities across those sequences. There's a simple Gaussian linking. It says double links. If you go up there, it will update the current heat map along with the stack bars. Let me see. All right. So the global view gives us a global view of the population, which is formed by the pairwise distances between sequences. You can think those distances as edit distances or Hamming distances or mutation distances. Right? You go and count the positions, number of positions where the two sequences have different values. Right? So based on these distances, right, we can think about different ways of filtering the data. So one filtering is what we call is distance to reference filtering. That is important for this data set because biologists generally would like to see how the mutations change with respect to the reference sequence, right? So user can you can interactively select the level set, the distance from the reference, and show and hide the other sequences in the population. And here we have probably more than 10,000 sequences. Once we have distances, we can think about other ideas, other interactions. One of the interactions we came up is not new in general other domains of computer science, but probably new for data visualization and interaction. So let me introduce epsilon filtering. So in order to understand epsilon filtering, you need to know what an epsilon graph is. Epsilon graph is a given set of data points. Epsilon 1 graph is the graph that you put edges between any two data points, where the distance between the data points is within epsilon. If it is 1, this is 1. So if you put the epsilon graph in this case, which is epsilon 1, basically puts edges, the distance between those data points is less than 1 or 1, then we put edges there, and then there is one singleton. Right? What is the point there? We have an implicit network here. Right now we are going to let users to filter this network dynamically. So one idea here is that you start with, when epsilon is 0, right, nothing is connected to each other. When epsilon is large enough, everything is connected to each other. In between, what you see is clusters based on connectivity of epsilon network. Right? So here I'm increasing the epsilon value, and while increasing the epsilon value, I identically color the connected components of the network. You can think as a clustering of the data set based on their distance or based on their similarity. And while we are coloring the points that are in the same connected network with the same color, right? This is going to give you, it's going to give you a sense of the space as you change the epsilon value. It's a multi-scale view of the data. And one advantage also is here that we use PCA. Of course, PCA is an approximation for two-dimensional mappings of similarities. And in this case, we are using the real distances. Now I'm increasing the epsilon value. All the epsilon is pretty high. At this level, it's still these two clusters. There are two clusters. They are not connected, although they are projected on the very similar place. So it's another way. This is a verification of your PCA projection, or if you are using another method, verification of your dimensionality reduction, how well it works. So let me see the video. Can I show you the video? Today. All right. So users changing epsilon value. Well, as you increase the epsilon value, clusters are happening. The clusters are constructed, and when you have very high epsilon value, almost everything is connected to each other. When epsilon is low, you have high number of clusters. What it provides is that it lets you to explore the high dimensional space of RNA sequences dynamically. So let's think about other interactions. This is one of my favorite ones. So once we have those sequences, right? Your RNA sequence is length of 200 in this case. We can think about defining the algebra on those sequences based on mutations. So I can say, given two sequences and mutations, those black bars represent the mutation locations. I can end them, right? Right. Ending might be useful for finding functional mutations. You go and interactively select a set of sequences and end their mutations. You will find the mutations that are common among all those sequences. And you can use OR with N to get neutral mutations. You can use OR with NOT to get conserved regions. So you can think about extending this algebra, but I'm going to show you the interactive version of this algebra. Okay, so user is going to select a sequence in the space, or a set of sequences, and our sequence map is updated. The sequence map is showing the intersection in the selected set, which is the ending of sequences. And in the end, you see that there is one mutation that is common to that selection. So if you think about this, so what we are trying to do here, so we are trying to give, there's a large collection of data points, right? I'm going to give you the global view with a simple projection. I have also local views and feature-based views, right? But since there is space in between these local and global views, I'm going to let you explore the space in between using dynamic filtering and other operations, which is here algebra on sequence is also a filtering. So it will let you to see, how those sequences relate to each other. So you can think about developing a language that uses this algebra. Semantics of that language for and, or, and not are kind of simple, but if you want to extend it more, you need to think about it better. Other thing was that one of our collaborators wanted to use this tool to figure out possible pathways between sequences. Pathways in the sense of evolutionary pathways, because there is some belief in that evolution occurs along one mutation pathways. So since I have an epsilon network, right? If I construct epsilon 1 network, which means that I have a network of sequences where the distance between, if there's an edge between two sequences, then the mutation between them is 1. And if I go and compute paths along those graphs, it will show me the potential pathways, evolutionary pathways between sequences. I'm going to show you our implementation. In this case, we are using, we are using shortest path. It doesn't have to be shortest path, right? Given the reference, I pick another reference, another sequence, and I can compute the shortest path. It's just a potential path. It's not a real evolutionary path, but it's going to let you to explore different paths interactively. So I can select the shortest path, and I can play the change of sequences along that path. One more time, construct the shortest path, and I play the path interaction, and I can show you interactively the change in the sequence along the path. Right. So we evaluated invis, the ideas in invis in a couple of different ways. We ask non-experts and experts to use the tool. Of course, we are still getting feedback from them. But another thing we did was to compare different encoding choices. One obvious question, it should matter. Whether it matters or not, we will see. All right. what we did was, I'm not going to talk about this user evaluation. I'm going to talk about the evaluation of numerical encoding. So what we did was we ran an experiment where we use our default encoding along with its permutations. And one observation we made that, one problem maybe, because when you give 4 to G, which has a different weight than, 0 to A. So maybe we can use binary encoding to have the equal weights for each base. So what we did that using different numeric encodings, we computed PCAs. Right? And visually, actually, there is no difference. And what we did also, we use multidimensional scaling on pairwise Hamming distances, and we get visually very similar results. So this is what we get visually. So because we are worried about if the layout, if the structure is going to change, if we change the numerical encoding, which it didn't. And to verify what we see visually, we computed pairwise rank correlations between those layouts, and they are very highly correlated. And the result, at least in this case, the numerical encoding really does not matter, right? So you expect it should matter, but it does not matter. And one reason is that the data has high correlations. It's very structured data, right? When you have higher correlations, when you have structure in your data, the encoding does not matter because those correlations dominate the structure, dominate the metrics. Right? When you have random data, then you don't want to look at anyways. Okay. There is no significant effect of encoding. All right, what's this? So what the point with the invis is that the existing tools, they are great for what they are designed for, but they are limited when it comes to exploring thousands of genomes simultaneously. And with invis, what we have is a prototype system where you can explore thousands of genomes simultaneously and interactively. And this is one way of approaching the problem. Show the global view, show the local view, right? Let user explore the in-between with interactions. And you can always put the feature-based views around those global views. Of course, let users drill down up in the data. The invis is open source. You can go and check it out. We are continuously working on that. I'm going to talk about a little bit that. But let's say moving forward. For invis, we are currently working on to make it useful for human genomes. So I would like to be able to explore large collections of human genome populations with invis. We are going to probably release a version of invis in January, where you are going to be able to visualize TCGA or 1,000 genome data sets with our tool. Of course, there are websites or databases where people go and upload their own genomes, their own SNP data sets. The other thing we would like to explore is to understand the social aspects of genomics. So we'd like to let people, individuals, to explore their own genome with respect to other people in their community or with their friends, maybe, right? Using invis-like application. Again, invis is web-based. You don't have to do anything. You just open the website. It's going to work. In general, in genomics data visualization, this is our observation. Interaction seems to be missing, right? So I'm going to show you one example. Interaction is very important. When you have large collections of data, you have limited visual space, sequence space. You have limited computing power. Then you need interaction to really expand those powers. So I'm going to show you one. When I tried to learn, when I was trying to learn a little bit more on genomics, I read this paper. I'm going to show you. All right. This is going to be proof. All right. So I read this paper. This paper was nice. They provided SNP data they used. They had also static PCA plot of the data. Here, data is SNP data from HapMap, mostly, I believe. And I got the data because I was trying to understand the field a little bit better and implement a little bit interaction. So this is a PCA plot of SNP data, and there isn't much surprising here. SNP variation reflects the geographic variation. So what I'm going to do, all right, so I can go and, this is not a real geometric zoom in. I have a PCA for that population as well. I can zoom in. People use those PCAs a lot, PCA plus a lot, but having a simple interaction actually changes in experience a lot. So often those, let me see, often those PCA plus use the first two components, principal components. What if I can change those components? What is going to change? This is simple, again, this is very simple. You can just adding a simple interaction is going to change the user experience. I can go, let's see, further. Oh, there is a substructure here. I can click. You have all the advantages of having web-based data visualization. All right. So interaction is very important. I think community should give attention to that. Interaction design is very important also. The other thing is that we, as a group, are very interested in perceptual foundations of data visualization. Right? In the end, data visualizations leverage human perception to facilitate your cognitions and then support data analysis. That's the whole point. But we don't know that's happening though. And you use a certain visual encoding, right? Let's see. I'm not sure this is working well or not. What are the, given alternative visual encodings of the same biological data, which one is better than the other? Right. So I think there is a great opportunity here to better understand the effectiveness of different visual encodings in genomics visualizations. To wrap up, so we have lots of data. Existing tools, by definition, are limited to, because they are not designed for that goal, limited to explore, let me explore those large collections of genomic data points. And invis is showing you one way of doing that. There can be many other ways of doing the same task. So to finish, I would like to thank my collaborators, basically. Jeff is my advisor and also collaborator. Invis, we implement invis with Jeff, Eric from Stanford, and Jeff from Cloudera and Mount Sinai. So thanks for your attention.